ladies and gentlemen. It's 5 to 10. We're about 5 minutes late to start, but as a first introduction and a welcome to Durham University, I've asked our Vice-Chancellor, Stuart Corbridge, to say a few words of welcome. Stuart.
Thank you very much, John, and a very warm welcome, everybody, to Durham University. It's not a splendid day outside, so it's as well that you're inside, and I'm sure that you're going to have a wonderful session. When I was thinking about this session, I'm delighted that we've got the University of the Third Age with us today. I was thinking really about great British institutions and modesty in a strange way, because I think at the moment we do feel a little bit under attack sometimes in universities, and there are very many institutions, I think, in the UK. I would think of the BBC, I personally think of the Health Service, Radio 4, the Open University, which seems to be under the cosh a little bit at the moment, the University of the Third Age, that are important institutions in our country and that stand for something really important, lifelong learning, peer-to-peer education, and engagement with important intellectual topics. So it really is very, very nice for me to put you all in that sort of loop and welcome you to the university today. Durham, I hope you know, although sometimes I think we're a very modest institution, which is a good virtue to have, nonetheless is an outstanding university and has particular strengths and always has had particular strengths in the sciences. And this is a story that I think we should shout about rather more, whether it's all the way from computational cosmology in physics through surface sciences in chemistry, through to the Earth Sciences Department, which is truly outstanding, on to engineering, computer science, biosciences and psychology. Some amazing stuff has gone on at this university over decades and is going on right now. So I think it's important to tell these stories at times and to celebrate institutions in British life that have continuity and that make a very large public contribution. So we're bringing together two parts of that loop, I think, today. We're very pleased, too, that the government now has got an industrial strategy. I think it's not before time that we have an industrial strategy in this country after years of not having one. And you will know, I'm sure, that there are 4 grand challenges which the government has identified. And 2 of those grand challenges are grand challenges that this university will contribute to very, very significantly. So in a couple of years' time, up the hill from here, I'm not sure if I'm pointing in the right direction, I've lost my sense of geography, but grandly in that direction, wherever the hill is, there'll be a brand new Department of Maths and Computer Science. With an innovation and enterprise hub for our students, because we're seeing very different students now coming to the university, many more people wanting to set up their own companies. Bringing business onto campus is a key initiative for a university like Durham moving forwards. But maths and computer science are 2 areas that we will be growing very, very significantly, doubling in size over 10 years at the university, and moving into more applied areas like artificial intelligence, big data, visualization, and robotics. And all of those things will have, I think, very important consequences for the North East, for County Durham. We're an ambitious city here, and it's an ambitious university sitting in an ambitious region. But the other one, the grand challenge that we can address most immediately is very much around clean energy. And we have tremendous expertise in the university, in engineering particularly, and in earth sciences in this area. Jon Gluyas, who just introduced me, is the head of the Durham Energy Institute, which is really an outstanding research institute linked through to major companies like Ørsted, contributing at the very cutting edge in this area of clean energy. And I know you're going to be talking about energy more generally. Andy Aplin, who's standing to his right, is the current head of the Department of Earth Sciences, in which John sits, and the current head of our Department of Engineering, Simon Hogg. I don't know if Simon's going to be here today at all. At some stage, was previously the head of the Durham Energy Institute. So, I mean, it gives me tremendous pride as the Vice-Chancellor that we have these great centres of excellence all across the sciences. I should say also the social sciences and humanities at Durham. But this really is a key area for the university, a key area for the country. So the fact that you're going to be talking about these issues today, I think is absolutely splendid. And it really does give me great pride as well to say it's wonderful to host U3A here today at Durham. I hope you all have a very wonderful day. You have to excuse me because I've got other meetings, but it's the sort of meeting that I'm sure I would like to participate in if I could. So thank you again and have a wonderful day.
Well, welcome everybody here today. I'd just like to say... Welcome everybody here today. I'm hoping you're going to have a wonderful day because I'm pretty sure you will do. I would like to thank the Professor for introducing us to the university and to this absolutely wonderful room. It's very cosy, isn't it? And it's quite interesting that the word energy is such a short word and yet it contains such an awful lot of detail in it and it has so many different aspects to it. And I'm hoping that we shall all learn something a great deal more from that today. This won't be the first time we've been at Durham University. We've been here before, well, not in this particular campus before, but we've been to Durham, and we've had something to do with the outreach programs in the university as well. And I'm damn sure it won't be the last one, will it? If you have anything to do with it, it won't, will it? No, so we shall certainly come again because we do enjoy coming here, and we certainly enjoy coming to the universities in our area. It makes us feel part of it all, and we're very grateful. Gentlemen, thank you very much for inviting us, and we're going to have a good time.
Okay, let the games begin. Oh no, that's not quite right, is it? Let me start, if I may, with a little housekeeping. You're currently in the Calman Learning Centre, and as I trust you all are aware now, you're on the second floor. The fourth floor, there isn't a third one marked on the lift, but the fourth floor is where we'll serve lunch and coffees. There are toilets in the stairwells. I'm not quite sure the male is one side, the female is the other, or thereabouts. We don't anticipate any fire alarms today. They've already been tested this week. But if the fire bell rings, we are obliged, of course, to leave the building. That will be done by the stairs. I know we have a number of people in the audience today who are less mobile than they would wish. And let me assure you that we do have the whole of the support staff in the building are trained to use the evacuation system, so you will be assisted. But we don't anticipate any problem. The meeting spot, should that happen though, is the surrounding the green just in front of the building. Is that it on housekeeping so far? Oh yes, indeed. Thanks, Lynn. What we are trialling today is lecture capture. And so the speakers will have microphones, and when we come to questions, I will ask you to speak into the microphone. That's being coupled with the slides which have already been recorded. We're trialling it because this is the way of the future. Students will be able to listen to lectures and see the slides I'll repeat things. I'm a little bit worried by this though, because I do remember when I was an undergraduate, one of my, I think, biology lecturers said, or maybe a chemistry lecture, the whole point here is to get what's in my notes into your notes without going through the brains of either. And I think we just delivered the technology to do that. So who knows? Okay, right. Let me introduce you now to what we're going to do today. So we have 4 sessions. Before that, a bit more on the Energy Institute. I'm getting ahead of myself. So the Energy Institute, as Stuart mentioned, is one of exactly 7 institutes in the university. So what is an institute? Well, we have departments. We have departments of maths, earth sciences, geography, sociology, anthropology, and so on, history. Where do the institutes come in? Well, they cross-cut all those different individual disciplines. So the aim of the institutes is to add value by integrating across pieces. So what you'll hear today, for example, is not just engineering, is not just geoscience, but the perceptions. How does society view various sorts of energy? You know, we can go back to the 1960s, and the campaign for nuclear disarmament also looked at the nuclear energy industry. Today, even in the last few years, we've had protests, of course, about the use or lack of use of fracking within the UK. And so the institutes cross-cut those boundaries, and many of us work in programmes which have multiple components. One of the large ones I'm working with at the moment, shared with half a dozen universities around the UK, brings together engineers, geoscientists, mathematicians, the business school, and indeed anthropology. And that's looking at the Centre for Energy Systems Integration across the UK. Okay, to today then. Well, I should say that about somewhere between 100 and 200 people in the university would claim to have a greater or lesser part of their life linked into the Durham Energy Institute. So to today, what we've designed is a programme divided into 4 parts, and the titles are there ahead of you. So overview of energy systems is what we kick off with, and we finish this afternoon on the social aspects. You'll get a series of short pictures, if you will, of about 10 minutes apiece from each of the speakers, plenty of times for questions. We've taken the questions that you provided to us beforehand and tried to answer some, or we'll address those in each of the different sessions, and we'll see how it goes. Enjoy yourselves. Well, I had a great time when I came to Sunderland. I was just saying to John before we came in that of all the times I've ever spoken to industrialists or students or academics, I've never had the grilling that I did from U3A. I spent longer answering questions, John, than I did speaking. I hope satisfactorily. So, let's have fun. And to do so, I'm going to invite the first 4 speakers to join me. So, Charlotte, Douglas, Andy, and Chris, isn't it? Thank you.
Is this on?
Check my list. Well, I can get that back. I've got it in red here. Okay. Okay, so let's start with the energy systems. I'd like to invite Andy Applin to give the first of 4 brief presentations. We'll take all 4 if we may, and then we'll take questions.
Yeah, okay. Can you hear me up there? The mics are working? Fantastic. Okay, and I can read my slides up there as well, so that's if I gaze into the distance, that's the reason. There's parts of me which kind of hopes that I'm part of the past, because fossil fuels have been incredibly important for us over the last couple of 100 years. We're in a period of transition, but they're going to be around for a little bit longer, that's for sure. So let me give me a little bit of context to start with, and this is just the obvious point that energy basically underpins growth. So this slide here, is there a laser working? Just about. So here we have GDP through time. You can see it's pretty constant until the last 150 years, and then it's really taking off, and that growth requires energy. The numbers there are the times it took the UK in our industrial revolution to double its GDP. At that time we had 20 million people, and it took about 100 years. The rate of change increases, and so move things forward a couple of 100 years. China, with 1,300 million people, doubled its GDP in 10 years. That is basically being fueled by fossil fuels in both cases. So the rate of change is increasing. The second general point then is that for each person who arrives on the planet, they will use more energy than the people who are here today. So on this graph, we've got people on the y-axis, and energy, it's in millions of barrels of oil equivalent, but energy, if you want, on the right. The yellow line is the one-to-one line. So if each new person used the same amount of energy, that would be the line. You can see then that the population from 65 to today has more than doubled. And because that line is below the yellow line, each one of those new people are using more energy. So more people, more wealth, more energy. And that's going to continue. For us then, giving it some context, so our industrial revolution was driven by coal. It's very appropriate that we're sitting here in Durham at the heart of, or part of the heart of that. You can see now going from sort of 1500 or so into the 19th century. So orange is coal. So you can see then that increase in wealth, increase in GDP in the UK was driven by coal. And you can see Italy was very, very different in that case. Exactly the same thing has happened in the last 20 or 30 years in China. So this is coal consumption. It's a couple of years out of date now. This came from The Guardian. The black line then is global consumption of coal excluding China. It's increased slightly, maybe by sort of 10% or so, but look what's happened to China. So it's more than doubled over a 10-year period. So that is what's actually fueling the energy systems in China. Others will probably say they're also investing huge amounts of money in other kinds of energy systems as well, but this has been the growth. And, you know, for example, China is building between 1 and 2 coal-fired power plants every week. Okay, this is an astonishing rate of growth. Moving on to oil. So it's kind of, you know, once upon a time it was wood, then it was coal, and then it's oil and gas. This is always a little bit scary, this. So, you know, it depends, because the angle of the black line depends on the x-axis. So you can just describe it how you want. But basically, this slide shows that not very much oil was being consumed before 1900, and probably not very much will be consumed post-2100. And I'm not prepared to look too far into the future, but this is a real snapshot of time in terms of human history. And when you unpick that in a bit more detail on the next slide, you'll see that most of the action is happening over about 100 years. So this one then, this is barrels of oil per year on the y-axis, and time from 1930 and projecting through about 2010 or so, this slide, projecting through to 2050. And this is what we would call, as geoscientists, conventional oil. So this is the oil that comes from the North Sea. It's the oil that comes from Brazil, from the Middle East. Okay, conventional oil. So we have production, which is here's the black line in here, and this is the discovery. And you know, it peaks and troughs depending on wars and when new provinces were discovered. But the production is probably the key one. And you can see then from about 1970 to now, it's kind of plateaued. It's harder to find big fields. And the projected finding then is declining very quickly through to 2050. Okay. So actually, from that 200 years on the previous slide, actually most of the action is over about 100 years, essentially, maybe a little bit more than that, on that order. Now, of course, new technologies come along and things change, and the one that you've probably heard of then would be things like shale oil and shale gas, what we loosely call unconventional petroleum, where we actually have to go in and fracture the rock. And these things do change, these graphs. And it is astonishing in the US what has happened in the last 15 years to modify that picture. Not radically change it, but to modify the picture. This is, so these are the various areas in the US where shale oil and gas is produced. This picture here comes from this area near the Mexican border. It's a great area to go and do some geology. It's one of the areas which has driven shale oil in the US. And you can take away from this picture, not a lot of people live there. Whereas here, a lot of people live. And that is an issue, of course, for us in terms of producing this. The graph on the right, then, is basically US oil imports and exports. And you can see, then, from 1973, this would be true back to the Second World War, that the US was a major importer of oil, with very important political consequences globally. The change here from about 2000 is entirely down to shale oil production. And so in about a 10-year period, the US went from a significant importer to a net exporter with significant consequences. We, for example, get liquid natural gas from Qatar, which originally was designed to go to the US. They have shale gas now, it comes to us instead. So, lots of political ramifications, I think, of that. So things change. So oil is still probably on the, on the decline, but new technologies come along and things change. Let's bring it home now and think about the UK and think particularly about shale gas, because that's kind of probably the most politically interesting issue at the moment in terms of UK, one of the most important ones in terms of UK energy. So the truth is that we import, 70% of our energy comes from fossil fuels, and for oil and gas, we import about half of that. We were self-sufficient in 2004. So 14 years ago, we were self-sufficient. We now import about half. This is a radical change. There is also, I've used the word sustainability, discuss what that means. But in this context, we've signed up to 40% CO2 reduction by 2030, 80% by 2050. That is a really big ask in terms of engineering and money. Not impossible, and we'll learn, I think, more about that today, but it's a big ask. And in terms of comparing the UK and the US, it turns out the geology is a bit more complicated. We have a high population density, and a lot of people don't want it to happen for a variety of reasons. And those that are sort of pro and against, those numbers haven't really changed very much in the last few years. But it's quite scary here in the UK. So this is for gas specifically. And we're saying now that about a third of our energy comes from gas alone. So forgetting about oil and coal now, from gas alone, it's about 1/3. 80% of our homes are heated by gas. The blue line there is UK production, the green line is UK consumption, and you can see that up to about 2004, there we go, that was the crossover point where until then we were producing basically what we consume, and you can see it dropping off here as the North Sea goes into significant decline. So we are now importing that gas, which is critical to our energy economy, from Norway particularly, and to some extent from Qatar. The other issue there at the bottom, if you can just about see it, is that we're also not very good at storing it. So when we bring it in from Norway or wherever, we have very limited storage. So if the supply goes off, in something like 10 days, we're going to feel pretty chilly. So very interesting sort of political comments. So what about, I've got two more slides I think now, in terms of shale gas in the UK. Is it going to happen? Is it not going to happen? We learn from the US. And these are data from the US. We have gas production from shale on the y-axis, and we're going from 2000, because the industry didn't really exist, the shale industry didn't exist in the US really before 2000. This is a real snapshot of time. And they have ramped up production to an unbelievable extent. So going from 0 to these sorts of numbers around sort of 30 billion cubic feet per day, the numbers probably don't mean very much. But interestingly, and this is from the US government, it's the Energy Information Authority, thinking it's going to be peaking somewhere around now and then declining steadily through to 2040. That's a lot of gas. How do they do it? How many wells are needed, and what can we learn from that? And this is where it becomes astonishing. So the number of wells is this black dotted line in here. So to produce what they're producing today, they have drilled, where are we, about 2018, something around here, they have drilled something like 100,000 wells. This is an astonishingly large industry. And you can play that in two ways. A big industry, jobs, money, but the other side of it is the environment. Do people want that to happen in the UK? And that's the discussion really, I think today. So here then in the UK, oh, that's interesting. Obviously I did it on a different, probably 4x, maybe this is 4x3 rather than 16x9. So the red area there should go all the way across into Lancashire as well. So if anybody here has got a Lancashire base, then that's where. So the shale gas area is basically a square across here. Don't worry about the geological cross section. But if you take some of the US data learn from that and then import those numbers to the UK and say it's going to be about the same. What do we need to do in this country in order to make shale gas a useful thing quantitatively for the country? This is not a couple of small companies making a few quid. Does it matter for us as a population? And I will reckon that in order to recover something like 40 trillion cubic feet, we use 3 trillion cubic feet per year, so that's about 13 years of our gas. Not insignificant, but not a game changer in terms of long-term going forward, I would argue. You probably need to drill something like 20,000 wells. Now, you can drill a bunch of wells from one pad, as we say, maybe half a dozen, maybe even 10. So we're talking about perhaps 3,000 locations. Can we do that geologically? Can we do that in terms of where the cities are? Et cetera, et cetera. But that gives you an idea about the scale of what will need to happen to really make this a flyer in the UK. And you can see then we've got a population of 8 million. And then, final thing then, in terms of history, we've drilled about 20 onshore wells per year historically in the last 100 years. So for this to happen, you have to ramp the industry up way beyond onshore what's happened in the last 100 years. And I think, John, that is my last slide, yeah.
Thank you, Andy. Yeah, I'm sure there are lots of questions which will come to you, Andy, when we get to the end of the session, so please do stay with us. Douglas.
Okay. I think this microphone is on. You can hear me? Okay. Thank you. Well, let me say how nice it is to lecture to a group of people that are really stimulated and interested by the subject. Normally I would lecture to 200 undergraduates in this lecture theatre, and by contrast they can be quite passive. It's also nice to get a round of applause before we've lectured, so I hope I live up to your expectation. I wanted to give some reflections and thoughts about energy from my perspective as someone who was trained as a physicist, but who is interested in energy from a range of different perspectives. And I also research into solar energy. So I've set this question: what is energy, how much do we use, and where does it come from? And I've got some thoughts about renewable energy and solar energy. So the first thing to say is there is a lot of rather loose vocabulary around the term energy. To a physicist, energy is conserved. We don't create or destroy energy, we convert it from one form to another. So heat, light, motion, electricity are all examples of different forms of energy. And of course we use energy to do all sorts of things. We use it to do work, and the definition that we would use in physics is force times distance. We use it to process information. The internet uses something like 20 to 30% of our electricity at the moment and growing. Refrigeration, transport, communication, and so on. So there are lots of applications of energy. And of course, for everything that consumes one form of energy or another, you have to produce an equivalent amount from a different source. Energy and mass are equivalent. I don't have many equations in my presentation, but this one is so well known it probably doesn't even count as an equation anymore. It's more of an emblem on a t-shirt. But you can see there that energy and mass are equivalent, and that's important as well when you think about processes like nuclear energy or burning coal. It gives you a sense of why you get so much energy from matter. So this illustrates, I think, quite nicely our energy challenge. You can see here an image of Western Europe at night. I've covered over the part of the map that we don't seem to be getting on with at the moment, but you can see that you can see sorry, I didn't really mean to say that. I hope this video is not. But you can see there, a very striking image that illustrates our requirement for energy. And it's quite interesting when you get involved in projects looking at energy in the developing world, the transformational nature of the availability of just small amounts of energy to illuminate houses so that school children can study at night and so on is really important. So that's a part of the challenge that we face. And of course, our appetite for energy is growing all the time. So we start with trying to give you a sense of some numbers. And I realize that not everybody may be familiar with numbers. As a physicist, numbers are part of our vocabulary. But if we take the sun as an example, so the surface temperature of our sun is about 5,700 Kelvin, or slightly higher in degrees centigrade, and that radiates 385 times 10 to the 24 watts. So if you manage a big light bulb, that would be the sort of total amount of energy coming out of the sun. And you can see here the solar spectrum goes from the ultraviolet, which is the very high energy, which does damage to skin and so on, and then we've got the visible part of the spectrum, and then we've got infrared down here. So the solar spectrum covers a very wide range of different wavelengths. And what I'm interested in is how you can extract energy from sunlight, or this electromagnetic radiation that is emitted from the sun. So if we come slightly closer to home, on our Earth, the amount of energy that is incident on the Earth from the sun has gone down by a factor of 1 part in 2 times 10 to the 9, you can see there. So we receive 175 times 10 to the 15, 15 or petawatts of energy is incident on the Earth from the sun. And of course that drives most of our climate. It provides the source of much of the energy we consume. Fossil fuels is essentially energy from sunlight captured over a very long period of time and stored in the chemical bonds. And nowadays, if you look at, sorry, my little laser pointer seems to have stopped working. But nowadays you can see that we get something like 1 kilowatt of energy per square meter incident on the surface of the Earth on average from sunlight. So there's a very large available resource of energy from sunlight that we can tap into and use to produce different forms of energy for our own individual use. And that's illustrated by the figure there, that the Earth receives sufficient energy from the sun in about 90 minutes to power the entire planet for a whole year. You know, so we have a very large resource that's available. So that's why we're keen to try and tap into that and use that. So we now ask the question, how much energy does our planet use? And it's very difficult to get exact figures because, of course, that relies on all sorts of monitoring regimes from all sorts of different countries and estimates and so on. But the best estimate is that the planet uses something like 17 terawatts of power. So that's 17 followed by 12 zeros. So if you imagine the consumption of the energy on Earth was represented by a large light bulb, it would have a power of 17 times 10 to the 12 watts. And of course, we have to power that more or less continuously, although it fluctuates across the planet as night and day rotates round and so on. But if you divide that number by 7 billion, which is the approximate population of the planet, that's equivalent to about 2.4 kilowatts per person. So that brings the numbers down to a regime that we're much more familiar with. And of course, that is not distributed equitably. Some countries, notably Canada and the United States, use far more energy per capita than countries, for example, in sub-Saharan Africa. So that's one of the challenges that we face. So here is a graph. This is taken from the BP Statistical Review of World Energy. They publish this on an annual basis. BP, being an oil company, uses units of million tons of oil equivalent here on the vertical axis. So 1 million ton of oil equivalent is equal to 11,600 gigawatt hours, for those of you that are more interested in those units. But you can see the challenge is shown here, that at the moment, on average, globally, only 3.2% of our total energy consumption comes from renewable sources. They've chosen to colour oil as green here, natural gas in red, and the coal is in grey. So you can see there's a real challenge in terms of reducing our dependence on those fossil fuels and growing our ability to extract useful energy from renewable sources. What's interesting is that energy is all about politics as well as about science and the engineering. And if you break down by geographical regions here, Europe and Eurasia, you can see that we have the highest percentage, 5% of our total energy consumption comes from renewable resources. What's interesting, you can see in the Middle East, they've got an almost complete reliance on natural gas and oil, whereas in Asia Pacific, they've got a much larger reliance on coal, you can see there. So again, much of the energy technology, the way it's used and implemented and developed, is a consequence of the political framework that is in place in particular countries. And of course, much of it is driven by economics. So this is a picture which is trying to show in a sort of illustrative, pictorial way the total amount of energy that is available to us from different sources. So it includes both renewable on the left here and the finite resources on the right. So effectively, the size of each of those circles represents the availability of energy. For renewable energy on the left, this is the annual amount. So of course, renewable energy is always available to us on a renewable basis. So the area of this circle here represents the amount of energy that the Earth uses in 1 year. I realize this figure is slightly different, but these are all estimates. So basically, what that shows is that the solar has a tremendous amount of potential and can contribute a very significant amount of renewable energy. Then we have tides, geothermal, hydro, biomass, ocean thermal currents. Up here we've got wind and wave. So you can see that each of those renewable technologies has a certain amount of energy that it's able to contribute. On the right-hand side, these are the finite resources. So these are natural gas, petroleum, uranium, and coal here. So you can see that if we were to continue mining the coal, we would have something like 70, 80 years worth of coal reserves if we used, or maybe slightly longer, depending on the proportion of coal that we would choose to use. So of course that means that in terms of making the energy transition, we have to move from renewable, non-renewable to renewable resources. So just a couple of pictures to show you the potential here. So here's a picture illustrating the potential of wind energy. And you can see that in Scotland there is a lot of potential here. The best in the UK, the wind speed on average is about 26 miles an hour, and that is equivalent to something like 1,800 watts per square metre. And of course, new turbines are getting larger and larger. You can see here that the newest turbine, this one would be an 8 gigawatt turbine, has 164 metre diameter. So that's pretty large when you compare it to the size of a jumbo jet. Here we've got a picture showing the potential of solar energy. So the important figure here is that the UK on average has something like 900 kilowatt hours per square metre per year of available solar resource. So if you do a simple calculation, you can see here that if you were to cover the roof of your house with solar PV, you would get something like 4,800 kilowatt hours of electricity annually. So this shows the potential of solar. The other point to make about this, of course, is that for many years, Germany here in the middle was indeed the world leader in solar PV because of political decisions made in that country. And of course, Germany doesn't have the highest solar resource. The highest solar resource is down in North Africa and Mediterranean. So this is just showing the first solar cell. So this shows some images of the solar cell that was developed in 1954. So it's taken a long time to develop this technology. So this is the first solar battery here, and the man is using it to transmit his voice with a microphone to a receiver over here. So by today's standards, this is not a particularly significant achievement, but it demonstrates how far I think solar technology has come. I'll skip over that because we're running out of time. So this just shows the growth of solar energy globally. So now at the end of 2016, we had something like 300 gigawatts of installed solar capacity. And the 27 figure is going to be about 390 to 400 gigawatts. Wind, we have about 540 gigawatts. So these technologies are already making a significant contribution to our energy demand in terms of supplying electricity. But of course, there is much further to go. And so this is just the last picture that I wanted to show. So this shows the kind of scale that we need. So one of the challenges of renewable energy is that it is low density. So for example, if you look at this picture, here is Ferrybridge C coal power station that's now decommissioned. When it was built, it occupies 1 square kilometre of land, and it produced 2 gigawatts of electricity. This is a utility scale being built in China, which occupies so much space. You can see it by satellite. There's the link up there. That's 850 megawatts, and that occupies 27 square kilometres. So the challenge with renewable energy is that we need very large amounts of area, either large area wind turbines or large area of solar panels to capture large amounts of energy. And of course that comes with the challenge of building that infrastructure and developing it and integrating it into our current energy system. So I think that's everything that I wanted to say. So thank you very much.
Douglas, thank you. I see that you, unlike the scientists on the picture there from 1954, you're minus a bow tie.
Well, I say that to students to set a new standard in dress. I didn't think there was much I could tell this group about dress.
Thank you, Douglas. Now, Charlotte, would you?
Thank you. I'd just like to echo Douglas's comments, and it's a pleasure to talk to you today and be here with people that we don't have to prize.
Oh, you're on yellow. It's on mute.
Is that better? That's better, isn't it? Sorry about that. So yes, it's a pleasure to be here with people we don't have to bribe to come along to listen to us. So thanks very much for the opportunity to talk to you. So I'm going to talk about developing a legacy. So first of all, to give you a bit of context to what I'm going to be talking about, let's go back almost exactly 160 years. The red circle on this plan shows you where Elvit Shaft was sunk. Elvit Shaft is actually in the atrium of the building opposite the gatehouse that you came through this morning. So we're talking about a shaft that was drilled in 1858, accessing a variety of coal seams. The kind of hatched areas on the plan there show what was worked, all beneath this site, and that's just on one seam, and that's at about 60 metres below us. There are 9 shafts within this kind of complex of buildings we're in today. We only ever found 8 when the buildings were being constructed. So do let us know if you find the 9th. So I'm here basically to talk about heat. I'm obsessed with heat, and that's really my thing. And the way I'm framing this is that if you look at how the UK's energy supply has been decarbonised to date, in terms of electricity supply, we have decarbonised round about 50% of our supply. For heat, you can see that our supply of heat from renewables is far, far less, and we're still heavily reliant on natural gas for the majority of our heat. And heat makes up half of our energy demand. So often when people think about renewables, they think about electricity, but it's really important to think about renewable sources of heat as well. So if you take that message home with you today, then my job is done. So I'm talking about the opportunity that we have within our historically abandoned coal mines. This could also be said of some of our metal mines as well, but today I'm focusing purely on coal. So you've got the map on the right, which was done for the UK government and shows you basically centres of heat demand, which unsurprisingly is located over many of our urban centres. And then if you just compare that with the map on the left, which shows you our former coalfield areas, we have a good overlap between the areas of coalfield and the areas of heat demand, apart from London, but we have theories about other sources of hot air we could use down there. So in developing a legacy, what have we got? We're thinking about the UK more widely now, not just here on this site. So 15 billion tonnes of coal were mined over the past century or so. And to put that into context, if we took that coal out, spread it over the land surface of the UK, you're looking at a layer that's about 5 centimetres deep. Why is that important? Because that equates to void space left underground. Admittedly, there will be some subsidence, so between a quarter and half of that void space underground will have been lost due to subsidence, but we still have significant void space underground because the mines are abandoned, pumping has stopped, they're now flooded with water. And we can use that water. It's sitting there at between temperatures of 12 up to 20 degrees in some areas. We can take heat from that and use that as a source of low carbon heat. We can also put heat back into the subsurface and use the mines for energy storage, which is something we're really interested in as well. And the good thing is that around 30% of UK homes overlie coalfields. And it can also offer a source of cooling. I mentioned that these mines are flooded. The Coal Authority is the regulating body for our abandoned subsurface and all the coal mines. They currently pump water out at several locations to stop unwanted emergence of mine water. And with what they're pumping now from several sites across the UK, the majority of which are in the kind of northeast area, there's 80 megawatts of heat currently just being disposed of to surface watercourses. So there's huge potential there, and they're very interested in this, and obviously we're talking to them about this. So why are we thinking about the mines? So I've already mentioned that they have the opportunity to supply and support and store heat. We've been a net importer of gas since 2004, and if we think about where our gas comes from, and some of my other colleagues have already touched on this, we're basically a net importer, so we are reliant on other areas. And the gas that we get through the European pipelines, some of that is also controlled by Russia. So we're thinking about energy security. Also, we have 17% of our gas coming from LNG. That has to be compressed prior to being transported. So it's a much more carbon-intensive fuel than maybe indigenously produced natural gas or gas coming through a pipeline. So we need to think about that as well. So how this could work, we've identified where the areas of mines were. They were incredibly well surveyed. We have access to the abandonment plans for most of the collieries in the UK via the Coal Authority. So we can drill boreholes. We can look at using existing shafts as well, but having looked at a few over the course of the years, a lot of them are filled with rubbish. So often it's better to drill a new borehole so you can have it exactly where you want it, have it close to the end user, which of course is one of the considerations for renewable heat. You can reverse it to provide cooling, so you can take heat from buildings and use the mine water to cool it, so the heat will go into the mine water and you put the mine water back underground. So it's all done through heat exchangers. There's no need to have mine water exposure at surface, and in fact you probably want to avoid that if you can. It just makes things easier. And there's no reason why you couldn't put other sources into the subsurface. So if you've got an industrial source of waste heat, that could be put into the abandoned mines as well to top up the reserve there. And one of the key things, we know we can do this. We've been drilling into mine workings for years. It's more complex than drilling into non-mine terrain, but it's easily achievable. We can pump water out. It's just getting people aware of this potential and also thinking that it's not risky. A lot of people immediately think of risk. It's a relatively low risk approach. The other thing as well is that there's heat in lots of things. So my glass of water on there it contains heat. It feels cold, but I could still get heat out of that by using a heat pump. And on the slide I showed you with the coal production, I mentioned that the temperatures were between 12 and 18 degrees, so you wouldn't want to be taking a bath in something like that. So you would use a heat pump to raise the temperature. And a heat pump works a little bit like a fridge. So if you go to the supermarket and buy a nice bottle of real ale off the shelf, and it'll be at the temperature of the supermarket, so maybe 20 degrees, 18 degrees, you want to drink it when it's maybe at 4 degrees or 6 degrees, although maybe real ale I think should be served a little warmer. So you put it in your fridge, and then you go back to it in a few hours' time, and it's, lo and behold, it's cold. So where has that heat gone? So the heat is why the back of your fridge is warm. So using a vapor compression cycle is the way the heat is abstracted from your bottle of beer you put in the fridge. The heat is rejected at the back of the fridge, and that's why your back of your fridge feels warm. And if you were to use this in a domestic setting, that warm bit at the back would be something like an underfloor heating system. If anybody wants to discuss the nuances of heat pumps, I'm happy to do that over a coffee. So this requires a new approach. We need to stop thinking that heat needs to come from hot things. So we've kind of, as the speaker from the history department will talk about later, we're talking about heat from fire originally, then we've used gas boilers. We've used things that have produced high temperature outputs. We talk about 80 to 100 degrees. Yet our living spaces are only heated to 20 degrees, and many hot water taps and things that you buy now because of building regulations are restricted to 38 degrees as well. So why are we overheating water to achieve heating of our homes? And we also need, as well as things to maybe changes in building control, changes in planning as well, so that areas that do have abandoned mines do think about this as a source. And one of the key things we need to think about also is retrofit. So the majority of our housing stock is older than 1965, and we'll still have 3/4 of that there in 2050. So as well as thinking about putting it onto new builds, which is often the easier way to start, we also need to think about how we could retrofit this to the homes and buildings that we have already. So there's several examples of where this works. The most local is Lanchester Wines, who have a large warehouse, which is a bonded warehouse for the storage of wine. You see there's a bit of a theme going here. And this requires a temperature-controlled environment, which is ideal for a heat pump. A heat pump works best the more you use it. It works most efficiently the more you use it. So temperature-controlled environments, such as archives, hospitals, any kind of food storage facilities, are great. The Coal Authority have a small system at one of the collieries where they're already pumping water that I mentioned before. We had the pleasure of visiting a super scheme in the Netherlands, which has my mortar at 28 degrees and heats over 200,000 square metres. So huge potential there. And the one that's been operational in Canada has been operating since the 1980s and was replaced a diesel system and paid for itself very quickly. So I did a case study of Spennymoor. So we had 200 homes planned for this area, and there's already one of these pumped discharges that the Coal Authority have. And we looked to see what was going on there, and we realised that we could meet the heat demand of these 200 homes with what's provided in the mine there. So the next step is just to try and convince people to think about this and incorporate this in their development plans. I'll skip that one as we're running a little short of time. So I just want to say really that we clearly need to think about decarbonising heat and changing and moving away from gas and thinking about how we store and provide heat and using low temperature sources of heat which are widely available. We've got abandoned mines under many of our population centres, so that's a really good opportunity for us there. So we've got ready-made infrastructure, given that we have little storage. In Andy's presentation, he talked about 12 days gas storage. We have little electrical storage yet on our networks. We have a huge potential for storage in this system that's infrastructure's there, full of water, ready and waiting to go. And if we connected those households I was talking about earlier, the ones that are overlying the coalfields, we could save around 11 million tonnes of CO2 annually if we use that resource. Thank you very much for listening.
Charlotte, thank you very much indeed. And the final speaker, when he gets the microphone or pointer this morning, is Chris.
So good morning, everybody. Can you hear me all right? Am I coming through loud and clear? Great. Well, I'm an engineer by background and training, electrical engineer. And I'm going to talk a little bit about a specific piece of technology and how we utilize energy rather than where we get it from. I'm not too concerned about where we get it from in this presentation here, but I'm concerned about how we use it and perhaps telling you a little bit about what I think some quite key challenges are that we need to try and address in the future. And that's all to do with electric motor technology, which is primarily my research area. So I've been involved in electric machine or electric motor research for a while in industry, but also here at Durham. So just to have a little bit of a recap, and I also lectured to 200 undergraduates in here on this very topic. But what are electric motors? Well, they're a conversion device. So, they're a physical piece of engineering. We take energy in and we produce some sort of more useful energy output. Usually that is electrical to mechanical. And in the context of most electric motors, that is rotary motion. So we use electricity to create rotary motion. And that is, you can think of many instances where that is going to be useful, primarily, around the home, but also in industrial processes. So electric motors make things move. And this is a picture of a fairly standard electric motor. So it's been sliced, it's been cut through the center of it. And I'm not going to go into great detail as to, you know, how it works and what is inside of it, although there is a, you know, key ingredients that go into making one of these electromechanical energy conversion devices. This one here, you might have heard the name before, which is an alternating current induction machine. So it takes in electric energy and produces a rotary output. We have something called a stator, which we use to create a magnetic field. We also have something that rotates, which is called the rotor. So the stator is stationary, it's fixed to the floor by some feet. And then we have a rotational part that's guided by two bearings that we get some useful output on. So we take in electrical energy, and we have some rotary mechanical energy output. Now that's very useful, but the thing I like to say really is that, you know, if you look in the northeast, you will find many factories. If you look in the UK and globally, you will find many factories. Very, very advanced modern manufacturing methods are actually underpinned by Victorian technology. So all of these electrical to mechanical energy converters, you know, they're Victorian. So they were invented in 1887, which is a fairly long time ago. But they've had widespread existence since. They were invented by Nikola Tesla. You might have heard of him. He was a Serbian/American inventor. So they use alternating currents. They're connected to the national grid, whether you get your primary energy from solar, wind, coal-fired power stations, etc. It goes into the national grid, and it goes into all sorts of things. Industrial drive, so in a factory you might want to drive a pump, you might want to drive a fan, conveyor belts, that type of thing. These devices are numerous in nature. We can also use them as generators, so for wind turbines, or even more modern is electric vehicles. So we can use that electric power, convert it to rotary motion, put a wheel on the end, and it will drive you along the road quite happily. An interesting fact, somewhere between 50 and 60%, depends where in the world you are, of all the electrical power that is generated goes into electric motors. Now, whether that's in factories or whether that is your washing machine, we don't split that up, but 90% of those are in industry. The three-phase induction machines invented by that guy. And their conversion efficiency, so that is how well we convert electrical to mechanical energy, is somewhere between 50 and 95%. The mean is probably about 85 to 90%. So at best, 10% of all the energy that we use. And bearing in mind that is a very large amount because 50-60% of all electricity goes into machines, we're wasting a lot of energy. And if you just look at a typical factory, so this is a picture of a pump type scenario. Hopefully this might work. You know, there's 1, 2, 3, 4, 5, 6. There's about 10 electrical machines, electric motors, in that very small corner of one single factory in the world. So, you know, they're very, very widespread. And every one of those, at least, is wasting 10% of the energy that it consumes. So it's typically the workhorse of industry, but, you know, we need to really improve that. So, are we wasting it? Well, the answer, of course, is yes. But how much? So we consume in the UK, to give a more specific figure, is 54% of electric energy or 15% of all primary, so oil, gas, etc., all those primary forms of energy, it's about 15%. And from the World Energy Outlook in 2013, there was prediction of figures of 8,000 gigawatts required in 2030. In order to fulfill the amount for electrical machines, or these electric motors, that is going to be 4,000. So, you know, it's a significant sum. And if we were able to somehow advance the technology from this Victorian hangover by 3%, and by 3%, that's not very much. So going from 90 to 93 is not a great technological leap. We could perhaps save in the region of somewhere 108 nuclear reactors from being commissioned around the world. So, you know, this is quite an interesting one. Why don't we just go ahead and do it? We could do a lot better, but perhaps the thing is, you know, we need some policy. We need industrial incentives to go away and encourage people to develop this technology, encourage factories who are typically very conservative in their adoption of technology to, you know, upgrade their machines once they have been developed. And now that is possible, it's technologically possible, but we need that policy there to do it. So all of these electric motors that we have, these Victorian ones, they produce a force which makes our rotary motion. We can do that in a number of ways. One way to do it, the modern way, is to use permanent magnets like you have on your fridge. So two magnets, they attract and they repel. That's a force. We can use it inside of an electrical machine in order to produce our rotary motion. Usually, the ones that are on your fridge are very weak. We need much stronger permanent magnets in order to create rotary motion in an electric motor. So we use these things called rare earth elements. And they're from a series of elements on the periodic table. They're called rare earth, but they're actually abundant relatively in the Earth's crust. It's just that they're not locally concentrated. So when you mine these things out of the ground, you typically need to mine quite a lot in order to get a very small permanent magnet. So we use specific ones, neodymium and dysprosium. We fashion them into magnets. We create some sort of high-performance electric motor, which can go into various applications such as wind turbines or electric vehicles. However, there's actually a big problem with this. So these two technologies here, wind turbines and electric vehicles, are seen as green. Well, if you mine a lot of stuff out of the ground, that's not particularly green. And there's a few things, different elements that they're usually concentrated with in the Earth's crust, like thorium, that are not particularly nice things. So perhaps that is a problem. Also, China owns about 90% of the economical reserve. If you own it, you control it. So in 2008, the price of these magnets went up by 3,000% because there was an export embargo and you couldn't get them. So, these types of applications, especially automotive, don't like that type of thing. So they're looking at alternative technologies, and perhaps they're not sustainable after all. In the long term, do we want to continue mining things out of the ground? And just to give you an example, wind turbine, 2 megawatt, very small wind turbine, contains about half a ton of this permanent magnet material. To get half a ton, you probably have to mine about 400 tons of earth. So, it's a significant problem. Electric vehicle has about 2 kilograms of permanent magnet, but really, are we thinking, is this sustainable in the long term? Perhaps not. So just in summary, to tie up, Victorian technology, we use it every day. It's very, very widespread to convert electrical to mechanical power. However, we need to change it. So we use a lot of energy. We need to improve the efficiency, so we need to develop the technology. But in order to take up its adoption, we need to really move policy forward. Modern alternatives, in order to try and combat this, using rare earth elements from the periodic table, is not, it's not a great way forward. They're considered green applications, but really they're not. So we need to have a rethink. So we need new technology options and good government policy. Let's discuss that. Thank you.
Chris, Andy, Douglas and Charlotte, thank you very much for the first session. Let's open up for questions. I do have your questions that were posted to us beforehand from Bernard, Christine and others, but we'll see how we go. Those in the audience, please feel free to re-ask them. Lynn, you have a roving microphone, do you?
I certainly do.
Okay.
John's going to do this side.
Okay, thank you. So, may we take a question? The gentleman here. Could you...
Well, just to hopefully get the ball rolling, one of the things that nobody seems to be approaching this by on a worldwide basis is to actually curb the rate of population growth. Now, I think that's a big challenge, but I think it's something some organisation like probably the ineffective United Nations maybe wants to take on board.
Yeah. I will offer that to the panel. I do have my... I play this game as well because clearly often we get the finger pointed at bad oil companies or bad nuclear companies or whatever it happens to be. But I say, and I say this with tongue in cheek, please accept that, it's the medics who are to blame. If we didn't have such good medicine, perhaps wouldn't be living quite as long, and we wouldn't have as many viable offspring as we do. And so, you know, whilst I agree it's an extremely valid question, there has been an experiment in population control in China, and it had unforeseen consequences, of course, with the disparity, the infanticide of the females. So I don't know if anyone else would care to dive in there. For me, you know, they're almost... we're not going to be able to solve those kind of questions without some enormous dictatorship, I suppose. But let's see. Andy?
Just one comment. It's not just the number of people that have to pursue
Yeah. Yes, please.
Okay, does this work? Yeah. Mo Brown, Newcastle U3A. Thanks very much. That was absolutely amazing. If we can, in 90 minutes, get enough energy from the sun, the biggest problem to me would seem to be storage. So you've mentioned one possibly safe method, not like lead-acid batteries, but what else is on the horizon? And is mining storage going to be very good?
Well, I think a number of people on the panel could answer. I'll start with Charlotte, if I may. Of course, you can say you don't want to answer it as well.
No, I had reviewed your questions, so that was one I thought I could contribute to purely on the heat side. But I think there's huge potential for heat storage within abandoned mines. It's something we're just not looking at, and it's there. It's good to go. We can use it straight away. It would be relatively simple to start using it. We can reject lots of waste sources to it. We can augment what's there, and we can take heat from it and put it back almost as we want. So I think it's got great potential, both in the UK and beyond. So I think for heat, that's a good way of looking at it.
Yeah, one of the ways we've been thinking about this storage, you know, where there is conversation around we haven't built battery storage, we don't have, you know, pumped storage is very low efficiency, gravity is not a great form of energy, but the way in which both Charlotte and I have been selling this to people is that effectively for the past, at least 200 years, we've been building the heat storage capacity in the UK by mining the coal. We just haven't commissioned it yet. So it is built, it just needs commissioning. Anyone else on Douglas?
Could I just add, it's the getting it from the sun into the mine that I was interested in. How are you going to do that bit?
Well, there are ways, I'm going to hog it for a bit. Like my wife, like me, is a geologist. She used to work on the west coast of Scotland during the summer, and on a sunny day, she would wash her hair. She lived on a caravan site which had a black hose pipe which trailed for about 200 metres across the grass. And she worked out that if she came back at 4 o'clock from the field on a sunny day, the black hose pipe would contain enough hot water, it was the only water source available, to be able to wash and rinse her hair. So there are certainly ways of direct conversion of solar energy into heat.
Yes, if I can just pick up briefly. I mean, I think you're absolutely right. The key issue with all renewable technologies is the fact that they're intermittent. We can generate electricity from the sun during the day, but not at night. It's not windy all the time, and so on. So I think the UK government has recognised that there is a pressing need to develop and invest in large-scale storage schemes, and that's part of the new industrial strategy that the Vice-Chancellor mentioned. In terms of the specifics of your question, storing electricity on useful levels is quite difficult, because we have, for example, there's a pumped storage scheme in Wales, Dinorwig, the Electric Mountain, and that is used pretty much every day to compensate for the peak demand when people turn on kettles and all sorts of things. But that was very expensive to build and a lot of infrastructure. And so I think part of the challenge is partly storage, it's also partly demand, what we call demand shift, so encouraging people to use electricity when it's more readily available. And of course, electricity is only one form of our energy. It's slightly less than a third, I think, of our total consumption. So heat is also another way in which you can capture energy from the sun. So solar thermal is also a technology that you can use much more efficiently than solar photovoltaic to produce energy. So I think there are a number of options going forward. In terms of large-scale storage, there are things like compressed air, there are things like storing thermal energy in large vats of molten salts. So these are all technologies that we're aware of, but the challenge is, I guess, growing them to a scale where they can make a useful contribution to our overall energy.
So I think 2 points for me from the engineering perspective is that, this is a relatively new problem, wanting to store large amounts of electricity to be consumed at a later point in time. So the national grid, was not set up to perform such functions. So we've come at it quite late, and the research is not, it takes time. Any new technology takes time to develop. So if you can develop something in a lab that has, 10 times more energy storage capacity than lead-acid batteries, that's fair enough. But in order to manufacture those en masse, distribute them, and make sure they're reliable for everyday operation over long periods of time, that is a significant challenge, and one that we haven't totally cracked yet. I think the second one is perhaps that some of the technologies that we're looking at, to think of batteries for one, lithium-ion type technology of batteries still requires what I call some special elements. So, these rare earths that I was talking about, you need lithium in there. So you need to mine something out of the ground. Is there enough in the ground? How do you recycle it? How do you get the energy density? Personally, I don't think batteries are the way forward. I think perhaps some sort of hybridized hydrogen storage. So what we need to do is produce hydrogen from electricity and integrate that into the gas network, because we have a much greater storage capability within gas, potentially, than having, very expensive batteries placed around everywhere that, only last so many hundred or thousands of cycles, which then need to be replaced periodically. So, and that is something I think is being considered quite seriously at the Rowlands Gill site in Gateshead. So it's getting there, but takes time.
Thanks. I saw your hand, Lynn, so I guess the gentleman next to you. Yes.
Hi. First of all, thanks. That was a really interesting sort of series of lectures there. And I think that I listened to quite a lot of that, and it reminded me of all the things I used to consider in the past when I was sort of involved with some of this. And one of the things was the 10% you were talking about of wasted electricity on motors and this kind of thing. And that, first of all, struck a chord that we tend to produce things for absolutely no reason out of all sorts of materials. I've got a little plastic key fob here, which we've all got. Some of them are just little dolls or whatever. You buy them in the pound shop, and if you look at how much energy that costs, and in terms of producing that, producing the plastic, the machines, the transportation, all the rest of it, for that thing, it's just a piece of useless design for our entertainment. And so looking at that point and coming in from the other end, someone mentioned population. With the industrialization started in England and then developed for the last 100 years or so, the population of the world is absolutely, well, we all know, exploded. And the consequences on environments all over the world in all sorts of ways. I know we laughed when we talked about that, but it's absolutely catastrophic. If we all lived at the same level now, and we all wanted to be communists and have exactly the same things, the present population in the world, I think, was worked out by, well, I'm not going to go who worked it out, but it was all sorts of different academics. We'd have to live like an Apache Indian. Okay? That's how it works out. Now, as this population increases and so on, and these other considerations we were talking about, if we're going to develop, first of all, are we working in a holistic way? Are we working, I'm listening to the energy side of things here today, but I haven't heard anything, and I probably won't unless I go to other lectures, coming in from the other side, how can we reduce our consumption of energy and live in a sustainable way? how do we want to expand as a human race, or do we just want to go into infinity with population explosions, using all the resources on the planet, and hoping we're going to all live on Mars someday? Now, if we had a sustainable situation and then move from there...
What I'm going to do, if I may, is hold that particular question for the full session. Clearly, Douglas would have something to say about going to infinity and beyond. But it's a very, very valid question. But if we may hold that till the final session. The gentleman, two gentlemen here.
Good morning, Frank Foster from Stockton. With the rise in EVs, we are going to have to need charging and refueling points. Unfortunately, I haven't got any anthropologists in here this morning, have we? I don't want.
We will have this afternoon. We will. Don't worry.
I don't want one of those things stuck outside of my door with all of my neighbours queuing up and wanting to use it to charge their car. You know, the logistics of these sort of things is just beyond me. And can I squeeze one quick one in for Charlotte? And I need your help here, please, John. If you recall, last year we had a talk from a postgraduate about the Clackmannanshire syncline, and he was saying that when he was looking at temperatures, he found that it was quite important to source out the tapping point. It wasn't an even temperature all over. And I got that sort of impression when you were presenting, Charlotte, that you were saying that the water was at an even temperature, irrespective of where you got it from in the mine. Am I right or am I wrong there? Please.
Charlotte?
Yeah, I think he was looking at...
That was Aaron, wasn't it?
Yeah. He was looking at deeper geothermal. So he was looking at where you would drill down maybe between 1 and 2 kilometres. So a kilometre you could expect the temperature to be around 35 degrees, and at 2 kilometres around about 70 degrees, kind of in this region. Now he's looking at deep geothermal, and we know how the temperature is going to increase with depth because of the geothermal gradient. What we don't know is whether we can find water there to get the energy out, because water is the energy carrier for geothermal. The rationale behind using abandoned mines is we know that those systems flow. We're not going to get water out at 35 or 70 degrees. If we did, it would be absolutely super. But we know it will be constantly between 12 and 20. The collieries deepen, the way the geology is, the collieries deepen towards the east coast. So the water that comes out the easterly ones is warmer than the westerly ones, just the way the coal dips.
Was he not tapping into those coal mines? Because there were a lot of old coal mines that are around that part of the Edinburgh centre.
I think he was looking at a deeper granite system, if I
He
recall
was looking
correctly.
deeper. There are coal mines. The point is, as Charlotte said, what we're trading off here is guaranteed flow for lower returns. So this is the widget building rather than the risky new iPhone or what have you. So that's different. I'll take one more question before coffee, if I may. There's going to be loads of time today. This gentleman here has been desperate for a few minutes.
Thank you, Mr. Chairman. A couple of points. I would like to comment on the population growth, which is a common theme we see in the papers and everywhere these days. I'm old enough, unfortunately, to remember 60 years ago when we were told that the population was growing exponentially, and in 50 years' time there wouldn't be room on Earth for anyone to stand. That hasn't happened.
Were they all standing on the Isle of Wight or the Isle of Man?
But the reason it hasn't happened is because in the developed world, people only have 2 or 3 children, so they are only reproducing themselves. Where there's not birth control, the population is a lot greater. So as countries improve and become more affluent, the population growth slows down and decreases. So one's got to look at this from a logical point of view. If I might go on to just a couple of other points that I put in, and I believe a lot of this confusion is about using energy and energy policy as a term. We've heard of a lack of energy or having to reduce energy. There's not a lack of energy. The world is awash with energy, as was pointed out in one of the slides. the sun produces enough energy in 90 minutes to feed the whole of the Earth's needs in a year. So there's not a shortage of energy. And I think a lot of the confusion comes from talking of energy. And what we should be talking about is commodities and energy conversion. And if you talk about commodities, it becomes more realistic. You can't go into a supermarket and buy a bag of energy. You can go into a supermarket and buy a bag of coal, or you can even buy a canister of gas if you want. So they are commodities. Energy isn't. And it's really the energy conversion processes, as we've heard about this morning, that are important. Now,
well, we will touch on that this afternoon as well. So perhaps it will be, if you don't mind, Frank, isn't it? It would be a good time to break for coffee. There's loads of time today. There are students, research students amongst us as well. Please use them, ask them questions. We'll break now. We can come back a couple of minutes late, can't we? So between we're now at quarter past, around about half past, if you can start coming back, we'll make sure we kick off at 25 to. Thank you.